HVAC systems are essential to any modern building. They provide a comfortable indoor environment no matter the weather outside. A well-designed HVAC system regulates temperature. It also controls humidity. Finally, it ensures good air quality. These factors are crucial for occupant comfort and health. A good HVAC system can also impact a building's energy efficiency. A poorly designed system can lead to wasted energy and higher utility bills. This is why careful planning and consideration of various factors are crucial in HVAC design. One of the most critical aspects of HVAC design is understanding the climate. We need to consider both indoor and outdoor conditions. This helps us determine the appropriate system capacity. It also dictates the best equipment for a particular location. Let's delve deeper into why geographic considerations are so important for HVAC design. Geographic location plays a significant role in HVAC design. Different regions experience varying climates. These climates directly impact the heating and cooling loads a building experiences. For example, a building in a hot, humid climate will require a much different HVAC system than one in a cooler, drier climate. Consider Oman. Oman has diverse geographic regions. These regions range from coastal plains to mountainous areas. Each of these regions presents unique climatic challenges. Understanding these regional differences is crucial. This knowledge allows HVAC designers to tailor systems for optimal performance. Let's take a closer look at the specific design conditions encountered in different parts of Oman. Oman experiences scorching summers and mild winters. The intensity of these seasons varies significantly across its regions. Coastal areas like Muscat experience high humidity levels. This makes the heat even more oppressive. In contrast, the northern region, including Musandam, has a milder climate. Engineers use specific design conditions for HVAC systems. These conditions represent the most extreme temperatures and humidity levels. Coastal summer temperatures can reach up to 45 degrees Celsius. Winter temperatures might be as low as 10 degrees Celsius. In northern regions, summer temperatures are slightly lower. They might reach 40 degrees Celsius. Winter temperatures can drop to 5 degrees Celsius. Southern Oman, including Salalah, has a unique monsoon microclimate. This requires specialized HVAC design for high humidity and rainfall. Understanding these differences is key for selecting appropriate equipment. It also dictates the sizing of the HVAC system for optimal performance. While outdoor conditions set the stage for HVAC design, indoor environmental control is equally crucial. Occupant comfort and health are paramount. This means maintaining optimal temperature, humidity, and air quality within the building. Room temperature plays a vital role in occupant comfort. Most people are comfortable between 22 degrees Celsius and 25 degrees Celsius, or 72 degrees Fahrenheit and 77 degrees Fahrenheit. Humidity control is another critical factor. High humidity levels can lead to discomfort, mold growth, and respiratory issues. Ideally, indoor humidity should be maintained between 40% and 60%. Fresh air ventilation is essential for diluting indoor pollutants. These pollutants include carbon dioxide, volatile organic compounds, and odors. The amount of fresh air required depends on the building type and occupancy levels. Air changes per hour, or ACH, is a measure of how many times per hour the air within a space is replaced with fresh air. Higher ACH values generally indicate better ventilation. Noise control is also crucial for creating a comfortable indoor environment. HVAC systems can generate significant noise, especially if not designed or installed properly. Selecting quiet equipment and using proper noise attenuation techniques are essential for minimizing noise pollution. Section 5. Chilled water systems, distribution and design. The chilled water distribution system plays a key role in cooling the air within buildings. It typically includes several essential components. Chiller, the primary device responsible for cooling the water. Pumps. These circulate the chilled water throughout the system. Air handling units, or AHUs. These distribute the chilled water to cool the air inside the building. Chemical dosers. These add chemicals to the water to prevent scaling, corrosion, and biological growth. Piping. This system carries the chilled water from the chiller to the AHUs and other units. When designing the chilled water system, the following criteria are crucial. The piping must be sized to minimize pressure drops, with a maximum of 39 kPa per 100 meters. For smaller pipes, those 50 mm and below, the water velocity should be designed at 1.2 meters per second. Larger pipes should not exceed 2.5 meters per second in velocity. The system design is focused on maintaining efficiency while reducing energy consumption and minimizing maintenance needs. Section 6. Air distribution ductwork and terminal devices. The air distribution system delivers and exhausts air within a building, ensuring proper ventilation. Key components include ductwork, air terminals, and fans. Ducts should be constructed in accordance with SMACNA standards and DW 144 guidelines. Air velocities should be kept within specific limits to prevent excessive noise and energy losses. For main ducts connected to AHUs, the maximum velocity should be between 11 to 12 meters per second. For fan coil units or smaller ducts, the maximum velocity is 4.5 meters per second. For extract and fresh air ducts, the maximum velocity should be 9.1 meters per second. Ducts should have turning vanes at 45 to 90 degree elbows to minimize airflow resistance and reduce noise. Flexible ducts should be limited to no more than 1 meter in length to prevent excessive pressure loss. Air terminal devices must be equipped with volume control dampers and sized according to face velocities. Pressure sensors should be installed within the ducts to monitor airflow pressures. These sensors should be connected to the Direct Digital Control (DDC) system for centralized monitoring and control. Section 7. Equipment capacity, oversizing, and derating factors. Selecting the correct HVAC equipment capacity is crucial for ensuring optimal system performance and energy efficiency. Oversized equipment operates inefficiently, cycling on and off frequently, also known as short cycling. This leads to increased wear and tear and reduced equipment lifespan. Undersized equipment, on the other hand, struggles to meet the building's heating and cooling demands, resulting in occupant discomfort. HVAC engineers use various factors to determine the appropriate equipment capacity. These factors include the building's heating and cooling loads, insulation levels, window efficiency, and occupancy levels. To ensure HVAC systems can handle future load increases and unexpected conditions, an overcapacity margin is applied during the design phase. A 15% excess capacity is added to the heat load calculations. This accounts for the natural aging of equipment over time and allows for unforeseen increases in load. Derating factors are used to adjust the equipment capacity based on specific operating conditions. For example, a 20% derating is applied at 55 degrees Celsius to ensure that the system can operate efficiently, even under extreme conditions. Section 8. Energy efficiency. The significance of COP. Energy efficiency is a critical consideration in HVAC design. Buildings consume a significant amount of energy, and HVAC systems are often the largest energy consumers within a building. Selecting energy-efficient equipment and designing systems for optimal performance can significantly reduce energy consumption and operating costs. The coefficient of performance, or COP, is a key measure of the efficiency of air conditioning equipment. It represents the ratio of cooling or heating output to the energy input. A higher COP means the system uses less energy to provide cooling, improving overall energy efficiency. For example, a cooling system with a COP of 3.0 provides 3 units of cooling output for every 1 unit of energy input. For all air conditioning systems, the minimum COP at 48 degrees Celsius should be 2.2 for all types of compressors. This ensures that the equipment is selected with a strong focus on energy efficiency, reducing operating costs, and environmental impact. Higher EER and SEER values indicate greater energy efficiency. Section 9. Air recirculation, balancing comfort and safety. Air recirculation is a common practice in HVAC systems. It involves mixing a portion of the return air, which is air exhausted from the occupied spaces, with fresh outdoor air before supplying it back to the building. This practice can improve energy efficiency by reducing the amount of fresh air that needs to be conditioned. However, air recirculation must be carefully controlled to maintain indoor air quality and prevent the spread of airborne contaminants. ASHRAE, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, provides guidelines on air recirculation limitations based on the building type and occupancy levels. Certain areas within a building, such as restrooms, kitchens, and laboratories, require dedicated exhaust systems to remove odors, moisture, and potentially harmful contaminants. Air from these areas should not be recirculated to other parts of the building. Instead, it should be exhausted directly outdoors. Section 10. Maintenance and monitoring, ensuring long-term performance. Even the most well-designed HVAC system requires regular maintenance and monitoring to ensure optimal performance and longevity. Preventive maintenance tasks, such as filter replacements, coil cleanings, and belt inspections, should be performed regularly to prevent equipment failures and maintain system efficiency. Building management systems, or BMS, are becoming increasingly common in modern buildings. These systems provide centralized monitoring and control of HVAC systems and other building services. BMS can track energy consumption, identify potential issues, and optimize system performance in real time. Regularly monitoring HVAC system performance is crucial for identifying and addressing potential problems before they escalate into major issues. Tracking key performance indicators such as energy consumption, temperature and humidity levels, and equipment run times can provide valuable insights into system operation and highlight areas for improvement. Section 11. Conclusion. Achieving optimal HVAC design. Mastering HVAC design is crucial for creating comfortable, healthy, and energy-efficient buildings. Understanding the importance of considering both outdoor and indoor conditions, selecting appropriate equipment, and designing efficient distribution systems are essential steps towards achieving optimal HVAC performance. In regions with extreme climates, like Oman, adhering to specific design guidelines and considering regional variations in temperature and humidity are paramount. By prioritizing energy efficiency, indoor environmental quality, and long-term system performance, HVAC designers can create systems that meet the needs of both building occupants and the environment.